Welcome to the CFA Colloquium. Very pleased to welcome Dr. Alan Rogers from MIT Haystack Observatory, who's going to speak about the EDGES experiment, the experiment to detect the global EoR signature. As many of you are probably aware, when the early gas in the universe was cooling and it had first been neutral, then it was heated up by the first stars, and you wind up getting this very remarkable absorption feature in the H1 line, which tells you exactly when the first stars and galaxies began to form. And Alan is going to talk to us about a detection of that feature and subsequent interesting excitement about the need to confirm it as well. But I really want to talk a little bit about Alan himself, who's kind of a remarkable guy. He was my mentor when I was a PhD student. He sent me a little bio, and it's very understated. I want to point out a few things about it. It says, Alan Rogers received the PhD in 1967 in EE from Massachusetts Institute of Technology. What he leaves out is that he kind of made his application through ham radio, because he was in Rhodesia, and he contacted a friend of his in Massachusetts. And the friend says, oh, you should talk to my neighbor who happens to be the foreign student admissions coordinator for MIT. And he did, and he wound up getting through ham radio an admission to MIT. That doesn't happen these days, needless to say. A little more rigorous, a little more formal, but that's how they rolled back then. And I'm very glad that Alan joined them. And then he says he aided in the development of VLBI for geodesy and astronomy. What that leaves out is that Alan really was one of the first pioneers of bandwidth synthesis, which allows you to make very, very accurate delay measurements looking at the background quasars, and enables you to triangulate the locations of telescopes on the ground and confirm things like plate tectonics. So he was one of the first pioneers in that field. And he also won the Grote-Reber Medal in 2010 for fundamental and seminal contributions to radio astronomy. So today he's going to talk to us about EDGES. Welcome, Alan.
Well, thank you very much, Shep. I'm very pleased to be here and show you some results, which we definitely have to confirm. They are important. I gave a talk on this, but before we had any detection. So some of the material I'm going to show you, you may have seen before. I'd like to dedicate my talk here to the memory of my dad, who was actually the one who taught me about radio, and to Professor Alan Barrett, who was my thesis advisor, who sadly passed away of cancer kind of early. And he was a great advisor. And also to my mother, who was the one who really encouraged me all along the way. And she passed away very recently, but just after celebrating a wonderful 100th birthday. So that was amazing. So I don't know how many of you have actually seen the paper in Nature. This came out in March. And ever since it came out, there's been a huge amount of activity and feedback and a lot of discussions and so on. So let me just try to explain this a little bit. This is the actual spectrum that we measure, but this is on a scale that's very coarse here. So you see the actual contribution from the foreground is about 3,000 Kelvin at 75 megahertz. Of course, you can't see any detail in here because of the scale. But then after you take out five terms that actually characterize in a way the foreground and the ionosphere, which I'll describe a bit more. This is what you get for a residual. So based on this fact that this still has a 87 millikelvin residual, we started, of course, realizing that there's something in there that we've got to understand. And so after much exploration of trying different functions and trying to see what might produce this, get rid of these residuals, we discovered that a best fit is this profile right here. And we're interpreting this profile. This is the actual model profile. And then what this is that profile with the residuals to the fit, these residuals added back in. So we actually are interpreting that as absorption that's being produced by the 21 centimeter line, redshifted to this frequency here, which is a redshift of about 17. So of course this is an unexpected result in that it's considerably deeper than expected. Most models, which I'll show you some of, would expect more in the order of perhaps as much as maybe 200 millikelvin, but not 500. And also important, I think, is that it has this sort of flattened shape, which is also unexpected. So having seen this with our first system, what we call H1 here, which is our what we call low band, and we plotted here, this again is strictly from my Nature paper, the same thing we show over here is shown again over here, and it goes from this light into the black here. But then we also show a number of different configurations of the system. For example, we show another spectrometer system, the same spectrometer system but operating on a larger ground plane, because originally we thought, we realized after some study, which I'll show you a little more on later, that a 10 by 10 meter ground plane was really not sufficient. We'd like to have a larger ground plane. So we have a larger ground plane. We have a larger ground plane and a recalibrated receiver. Last time I gave a talk about this edges technique, Erwin Shapiro strongly recommended that if we observe something with a receiver that's being calibrated in the lab, and then we get something in the field, we need to obviously take it back to the lab, recalibrate it, and check that we really have a consistent calibration for that data. And now we've done that kind of recalibration several times. We've also been very much concerned about the antenna configuration. Could that be causing this particular feature, profile of absorption? So we've reoriented the antenna. This is called low 2 just because it's actually a different antenna that's on a different ground plane, but we've reoriented it from north-south to east-west. We've taken off the Balun shield. We've done a huge number of tests, which I will describe in a little bit more detail. So this is sort of a diagram, in a sense, that sort of puts what we're seeing in a somewhat larger perspective. And I'll later on, I may go to an even larger perspective in terms of covering a wider range of redshift. But what this shows on the top starts right from the Big Bang, goes to the present, but actually blows up here in this from 100 million years since the Big Bang to 1,000. And what we have seen is in red here, this absorption. And what I'm showing here in blue is close to what you might expect to see based on the theories that are currently, there are a lot of different parameters that we can look at, but this is typically what you might see. You might see an absorption here much weaker and broader without any flattening, and then later on some emission. We have not detected any emission at this point, although further along, maybe a system could ultimately detect emission as well as absorption. Down the bottom here, I try to explain a little bit what's going on. Why is this an absorption? Well, it's an absorption because the hydrogen line itself is being initially over here. The hydrogen line is coupled to the CMB, but then comes down. Later, I'll show a plot which goes further back. But the way the absorption is produced is by having a spin temperature, that spin temperature being determined by the relative population of the energy levels that form the 21 centimeter line. And when the spin temperature, or in other terminology, what's often called the excitation temperature, drops down below the background, which is, in this case is the CMB, you expect to see absorption. And then later on, if that spin temperature changes to be above the background, which in this case is the CMB, you'd expect an emission. So this is a typical set of absorption curves that were produced by Pritchard and Lowe back in 2011. And this is pretty much what we expected to see, this black curve here. There was a modeling here that produces a greater depth, but still nowhere down to the 500 millikelvin. And then here, the absorption. So I just want to give a little bit of history here, going back a ways. I didn't know about this, but I discovered, after our paper, that in fact somebody had actually predicted that there would be absorption from the 21 centimeter line at high redshift. This goes back to 1977. The basic theory of why the spin temperature would get coupled when the first stars light up by the Lyman-Alpha radiation was actually proposed in 1952, and a paper which gives all the details published by George Field in 1958, showing that what's going on here is sort of like, in some sense it's like a pumping action, but it's to make a maser, the way you do is you have these transitions in such a way that it overpopulates the upper level, then you get a maser. In this case, this coupling is actually moving the spin temperature so that it equals the kinetic temperature. So when this effect dominates, the spin temperature should equal the kinetic temperature. Now, going into a little bit more detail about what all the things that we've looked at. This shows our estimated uncertainties of various quantities. For example, the reflection coefficient of the low noise amplifier, and both in magnitude and phase, the antenna reflection coefficient, and the phase of that, and here they've been increased to larger values. But basically, what I want to show here, and I'll give you a little bit more insight into this when I show you a little more about the hardware, is that it seems like no matter what we do, if we change our instrumental parameters, even with fairly large terms that we think are much larger than they should be, we still end up measuring this roughly half a Kelvin absorption. We basically can't get it to go away, if you will. This gives more detail of, I mentioned all these different configurations. There are some additional ones here that I didn't say. We in order to get a calibrated spectrum that's not affected by the beam effects of the antenna. Our antenna is not perfect in the sense that its beam changes with frequency, and that change of frequency introduces a systematic effect. But we find even when we make no correction for that, we do get not the same. We clearly that's clearly a very important factor, because it does influence what we're seeing. But that's with no correction at all. We've also tried different modeling. We model the beam with with EM electromagnetic software, most of which we've done with this FICO, which is a commercial EM package. So other terms that are important here is we've worried about could what we're seeing be somehow the result of interference. In particular, for example, of interest to some might be, are we seeing something that has to do with reflections of all the radio signals on the globe coming back from the moon? And in truth, we do have a small effect. We can see, I'll show you in detail later, the effects of the radio interference which is reflected from the moon, which we see when the moon is above the horizon. The other very important test we've done is to show that this absorption profile that we see is global in the sense that it doesn't change with the local sidereal time. So, for example, when the galaxy is up, we get a higher sky temperature. This is in 6-hour average bins. Later down here is in 4-hour average bins, but you can see the higher temperature does not produce a higher absorption. For example, if that absorption were coming from some effect in the atmosphere, for example, or from many instrumental effects, you'd actually expect that absorption to go up with an increase in the foreground, but it doesn't. So it does behave just like it is a global absorption profile. This just is another way that many times we look at our data, and that is just to display in one dimension here, where we show as a function of frequency and find the best absorption. What would we get for a signal-to-noise ratio? And as you can see, we've got extremely high signal-to-noise ratio. And we go from the, this is a residual, in this case, with only 4 terms renewed, but only 4 terms because we're covering a smaller frequency range here of 60 to 100. But you can see how that residual basically drops down to the noise level for the best fit, and here the parameters are given down here, which are close to the nominal parameters. Here's a MCMC analysis showing that even though we get this very nice high signal-to-noise ratio, and it looks like we've got very solid detection, how well can we really determine the various parameters that we're solving for? For example, how well can we determine the flattening parameter? Now we use what we call a tau here, because we're actually modeling the flattening as if it were very high absorption. If you're in spectral line astronomy, if you get a very high optical depth, you get a saturation of the absorption. And we're using that same factor, that tau factor. We're not expecting, I'll discuss this later, that we see that flattening because we are in fact looking at a very high optical depth. We have another explanation for it. But we use that parameter. So our nominal parameter of about 5, you can see that, with this uncertainty here, which goes up to 95% here, that it could be as high as 12, or it could be down here at about 4, and so on. You can see the errors in the other parameters. And here's just I show that I've used a different analysis. I've used a delta chi-squared analysis with producing a similar sort of sets of curves. This is my own software. I'm not very terribly happy with this. Recently, as you probably already know, we've had some feedback with the group under Richard Hills at Cambridge University. And he's been looking at our data that we've released with a program called Polychord, which I'm very anxious to get my hands on and test, because it seems to give some rather nice results. It certainly makes very, very beautiful plots. And as you can see, my plots are not very good. But again, it does show that, we have a considerable uncertainty in some quantities. These are for the two different systems, and they don't have the same amount of integration time. So the parameter that which is least well determined is that degree of flattening. Just to give you now to look more at the instrumentation and sort of explain a little bit of the evolution of that instrumentation. This is what we call edges 1, and in edges 1 we did not have what we now call absolute calibration. We built a system where we tried to make everything as broadband as possible, as smooth as possible, and so we made all those measurements, and with only relatively crude calibration we used that to measure the spectral index of the foreground, and we got a fairly substantial error in that. But this was with basically only partial calibration. Using that system, we were able to put some limits, although not terribly interesting ones, on the emission, which I discussed, but we would only have detected emission if that emission feature was extremely narrow in width. And so this is a paper that was publishing those limits, but there were certainly no surprises here. And as you can see, our width is very narrow, and that is certainly not expected. If there is absorption out there as expected, it would be much wider in bandwidth. So edges 2 is what we're using. It uses broadband compact dipoles, reflection coefficient typically better than minus 15 dB. It covers the 50 to 100 in low band and the 100 to 200, and of course I'm talking primarily today about the 50 to 100 megahertz. It uses a 3-position switch to take out the bandpass effects. The lab calibration of the low LNA noise waves and internal noise diode. It uses noise diode calibration, the calibration of the noise diode itself, if you will, using a hot and ambient load. And the performance verification in the lab is using what we call an antenna simulator. Basically, an antenna simulator is something that has a reflection coefficient that's similar to the actual antenna we have in the field, but instead of having the sky as the source, we have a hot load or a noise source as the source, and then we put that through a set of filtering and cable in order to try to simulate the various effects of the reflection coefficients from the antenna and from the LNA to verify that our calibration is good. This is what one of our antennas looked like, assembled, being tested, or initially tested at Haystack Observatory before being shipped to Western Australia. Here it is in Western Australia. Up here you can see this is after we extended the ground plane from the original 10 by 10 meters out to a much larger size. And in addition to extending that ground plane, we also perforated the edges of the ground screen, and that basically what that does is any reflection from the edge of the ground plane basically undergoes a phase shift and tends to become less coherent. And this is not a technique that was invented by us. This is a technique that was developed for the various national facilities that are used to test antennas in order to reduce the effects of reflections from the edge of the ground plane. It shows the antenna here it uses a Roberts balun, and here's a shield. Now, we were concerned, one of the tests we did, we were concerned that somehow maybe the shield produced resonances, and maybe what we were seeing had something to do with the shield. So one of the tests we did was to remove the shield, and basically we still get the same absorption feature. Shows a bit more detail of a whole setup. Here's a high band antenna. Here's one of the low band antennas. Here's the control hut in which the electronics, what we call the back end electronics is located. Here's another picture of the low band antenna. Here's a picture of the receiver prior to installation. Here's a picture of the site from Google, showing that it's actually large enough that you can see it in Google Maps. And this is a more explanatory diagram of what we really have, with some detailed pictures. Maybe let me first start by just pointing out these pictures. This is the connection on the Roberts balun that's illustrated diagrammatically up here, this connection here. This is the connector, the balun, which it converts from unbalanced to balanced 50 ohms, and this is its connector. When this is installed, is that this connector mates directly with the receiver, and the receiver is located under the antenna. In order to get what we call absolute calibration, we define a reference point right here, and we have switches built in so that we can connect a vector network analyzer system to measure the reflection coefficient of the antenna itself. Then we switch this over in order to connect the spectrometer, and the spectrometer has what we call the three-position switch. It looks at the antenna. It looks at a load, which is basically the ambient temperature of the receiver, which is 25 degrees centigrade. And then it also looks at a noise source turned on. And I'll try to go through watching time here a little bit, just to pick out points fairly quickly here. Some of the innovation here, we found that the regular vector network analyzers were really not accurate enough for our purpose, so we thought at one time of building our own, but we quickly found out that we could actually improve the performance of a vector network analyzer, which is limited by its calibration load. To calibrate a vector network analyzer, you have a short open and load. When you get that load from the manufacturer, they basically tell you it's perfect. It's a 50 ohm load, and you just assume that, but it's in reality it's not. We came up with a technique where you can take enough measurements by using an asymmetric two-port network in order to solve for the impedance of the so-called perfect load and characterize it. That includes these measurements plus an actual resistance measurement of the load itself. And this paper is published in this journal. This just goes through the math of what we have to do here. We have to measure the antenna reflection. We have to measure the reflection from the antenna and also the reflection from the LNA, and we measure that at this reference plane interface. And this is the math that's involved. Looking at the time, I think I have to skip along here just to show you that we do have all the mathematics we need to do this, and to also correct for the fact that a low noise amplifier not only amplifies, but it also emits radiation that goes out to the antenna and gets reflected back. And there's actually two parts to that. One is noise that gets reflected back but is uncorrelated with the noise that comes out of the LNA. And there's another portion which is correlated with that. And those two pieces have to be separately determined. And here is the mathematics in order to do that. And then, as I mentioned, we have to do the three-position switching. So if you concentrate down on this formula here, it shows that when we measure the power on the antenna, or the spectrum on the antenna, if you will, spectrum on the load, we divide by the difference between the spectrum looking at the load plus the calibration, noise source turned on, minus the spectrum on the load. And when we do this division here, it basically cancels out this this gain factor. So, for example, in any typical spectrometer, it normally has a bandpass filter and everything. The effects of the bandpass filtering are taken out by this 3-position switching. We also, of course, have to correct for the loss in the balun, for example, and any loss in the antenna. We have to correct our data for that, and this shows a relationship to make that correction. This is a summary of our calibration procedure. So in the lab, we measure the reflection coefficient of the LNA, we measure the reflection coefficients of the hot and ambient load, and the open and shorted cable, an open and shorted cable, which I'll show you, used to measure those correlated and uncorrelated noise from the LNA. We measure the 3-position switch spectra from the hot, ambient loads and the open and shorted cable. We use this data to calibrate the internal noise source and measure the LNA noise waves. We measure the balun loss. And then in the field, we have the capability of measuring the antenna S11, as I explained with that switch. And then in simulations, we can estimate the antenna and ground loss, obtain the sky spectrum, and use that to obtain an absolute calibration. Using the lab data and so on, we obtain that sky spectrum. And then, as I explained, we still have to use basis terms to take out the effect of the foreground and the ionosphere, and then solve for the line signature. And there are some additional steps that we may need. We, for example, have tested, we don't frequently measure the antenna reflection in the field. We only do it periodically. But we have, for example, done checks on remeasuring the antenna reflection coefficient, for example, under different weather conditions. If we suspect that there might have been some change that might have taken place, we remeasure the antenna reflection coefficient in the field. And as I mentioned, we can't recalibrate the receiver in the field. We have to bring it all the way back to the lab and recalibrate it. We correct for the antenna beam shape changes versus frequency using electromagnetic simulation and a sky model. And I mentioned that we use an antenna simulator to test the accuracy. And the assumption behind the simulator is that a matched load at a uniform temperature is precisely equivalent to a lossless antenna observing a uniform sky at the same temperature. But as I mentioned, we do try to make that antenna simulator have characteristics in terms of reflection coefficient that's very similar to the actual antenna itself. This shows a picture of our calibration load in the lab. This is a load that can be heated to either form an ambient at an ambient temperature or up to about 200 degrees centigrade to provide a hot load. These, as I mentioned, the open and shorted cable that we use to measure the antenna reflection coefficient. To measure the noise waves. And here's a picture of the installation again. This shows a little bit more detail of the receiver underneath the antenna with the cover removed. And I'll go through some. These are the physical functions that we use when we do a 5-parameter fit with physical functions. One of the things that's been that we realized and has been emphasized to us by the group from Cambridge is that yes, we use these, but we don't actually get really very meaningful values for these physical parameters because they also soak up some of the instrumental effect. We can, however, and have measured the effects of the ionosphere by using different spectra. So in this case, while we can't solve for all those parameters and get good numbers for the ionosphere, if we look at differences, we can solve for the opacity of the ionospheric changes that take effect, and we can also track them, and we can measure the temperature of the ionosphere when those perturbations change in opacity. In the long run, maybe with better calibration, we can do this on the atmosphere without having to rely on a reference from a previous time in order to handle just perturbations. This is the what we call the beam chromaticity. This is the change of beam, which occurs with frequency that we have to correct for. And this shows that extended ground plane with some numbers, which I don't think I have time to go in detail, but basically showing that we get a lower contribution from the ground plane the larger we make it. Of course, ideally we'd like to make it even larger, but practical limitation. This is roughly 30 meters by 30 meters. This just shows, the difference between what we would get by simulation. This is an infinite ground plane. This is with the 10 by 10. This is now as a function of galactic hour angle. So when the galaxy is down, we don't have much effect in beam chromaticity at all. It's only when the galaxy is up, and especially when the galactic center is overhead, that we get a significant effect. And it also, of course, we show here differences between the case of the extended ground plane and when you change it from one direction to another, it changes somewhat. We have actually measured the foreground as best we can with the current system. This is currently mostly data from the high band from 100 to 200 megahertz, and we get pretty good agreement with the Guzman foreground model, which includes 45 and 408 megahertz, but not so good agreement with data that in the so-called standard model that doesn't include the 45 megahertz data from Guzman. Again, this is, I showed the best fit absorption. This is to illustrate the effects of radio interference from the FM signals, and basically this is just showing these are the residuals, again without solving for the absorption, but it just shows the effect of the radio FM interference, but it also shows that we can take it out, and fortunately FM radio is not digital yet and has carriers, so you can actually, if you just take out the carriers, you're left with enough spectrum that you still get a reasonable spectrum. Once it becomes digital, that will be difficult to do. And again, I've tried to summarize all the various things that we've tested: sensitivity of receiver calibration to reflection measurement errors, recalibration, Irwin-Shapiro's test, changed antenna orientation. Used data from two separate antennas on different ground planes, changed the ground plane size, removed the Balin shield, measured the absorption line over a full range of LST, checked for effects of ionospheric absorption and emission, which we do see, but in general, those effects on the are relatively smooth and have a very small effect on the absorption profile. And we've checked on RFI effects. We've done some testing of our sensitivity to foreground fitting. We'll probably be doing more of that based on some comments from the Cambridge group. We have two independently developed processing pipelines, Haystacks and ASUs. We've checked the effects of processing data with calibration made at different temperatures, just to make sure that our calibration is not extremely sensitive to errors in temperature, because we will, even though we control the temperature of the receiver in the field, there are still some effects of temperature that we could probably improve on. And we've also checked on the effect of that absorption feature that we see is not influenced by the loss in the balun. We have an extremely low loss balun, but there was still some concern that that might be contributing at least to what we see. I'd like to move on now in the remaining time here to emphasize that we need confirmation. These are the other systems that could potentially confirm what we see. The SARAS-2, which is the system of Ravi at the group in India. This is a system that's being run in down south of Cape Town on a remote island. This is the system that's developed here, LIDA. And I mentioned DARE here, but I think the latest word on DARE is it's probably not going to be a project. I think it's it's basically being declined by NASA at this point. This shows pictures of those systems. The PRISM system is very similar to ours. I'm not entirely sure of their calibration. This was a system. This is not actually a good picture of a current system. The Bighorn system was a system that was developed in Western Australia, but is not currently being developed any further. This is the LIDA system at Owens Valley, and this is the SARAS system developed by Ravi and group in India, and it's a rather different system, and relies on the fact that the antenna is electrically small, and so the beam effect on this has an extremely constant beam width frequency, so there would be no longer any concern about beam chromaticity effects, although I might be a bit worried about chromaticity effects due to what might be below the soil here, if there's any rock or anything below that might produce reflections that would produce chromaticity effects. But it is a very different system, and they've already published some good data in the high band with low enough residuals that I think this system has potential for confirming what we see. This is just a little bit more summary. I'm a little bit concerned about digital TV at Owens Valley, and that's only 40 miles from Owens Valley. I'm not sure. I know they do see that signal occasionally. I'm not sure how much of a problem it is. This is not published, but this does show a hint of the same signature from a different end, completely different, well, completely. It's a rescaled antenna. It's what we call mid-band that covers this frequency range I've shown you, 60 to 120. And it is showing what looks to be very similar in parameters to what we see, but you see all these ripples in here. Those ripples are because of a mistake that was made in the construction of that receiver with an incorrect voltage regulator that we have to fix, and it has been fixed, and this antenna we hope to redeploy in the next few weeks. This is even more, this is really a little bit very marginal, I would say, but there is a hint that we see a same signature in data that was taken by Edges 1 back in 2011, 2012. That system is very different. I showed the system. It's not absolutely calibrated. It just uses a very smooth responses. And because it's electrically small at this frequency range, it's hard, the data gets much noisier down here because the reflection coefficient is so high. But it is showing a hint that that same signature, although there's some ambiguity, if this is really correct, and it's not really much higher than this, then this is basically, I would say, consistent with what we're seeing. So now I'd like to just move on to some possible explanations, and maybe some more discussion, because I'm watching that time up there.
Don't watch the time.
Well, we want to have time for discussion, right? And I'm presuming I don't have. I should start discussion in the next few minutes. So, okay. So the possible explanations are that there's interaction of dark matter with a hydrogen that's lowering the kinetic temperature down from 3 Kelvin to 1.5 Kelvin. This is published in the same issue of Nature. There's other suggestions that maybe we see a stronger absorption because there's more than just the CMB that's being absorbed. There's other radiation, additional radiation out there that makes for something much higher than 50 Kelvin. We'd have, for example, if it was another 50 Kelvin from something else, then the absorption depths we see would be expected, or getting to the point where it might be accepted. But of course, this wouldn't not explain the flattening that we see. There's also a possibility that there's more baryons in the universe than we think. Possible explanation of the flattened bottoms is, at least my explanation is that it's, and I think this is most likely, that we're basically, quote, bottoming out on the kinetic temperature. The spin temperature is bottoming out at that temperature, and I'll show you a plot of that in a moment, or I guess an illustration. Another possibility, which I think is unlikely, is that there's some kind of clumping of the hydrogen, and that what we're seeing really is a very high optical depth. But I think that's unlikely. This is an illustration. I want to emphasize this is just an illustration. I have not done any new physics or anything here. All I've done is to take what's out there. This is, I think, the accepted curve for what this cosmic background does. And I'm going all the way here from redshift of 1400 or so to redshift of 13. And this shows the lowest current models that I've seen have a kinetic temperature getting down maybe to close to 3 Kelvin. So with a 3 Kelvin coupling of the spin temperature to the kinetic temperature, you would get this absorption here. If the decoupling of the kinetic temperature from the CMB occurs earlier, as it is expected to be the case if there's dark matter involved, for example, then this kinetic temperature drops down further because it's got a longer time span in order to drop down. And if it got down to about 1.5 Kelvin or so, then you could get an absorption that looks like this. But in order to get this flattening, what I've had to wave my hands and assumed is that somehow we get a very strong coupling, with enough strength and enough delay here in the heating that we get this period where it basically flattens out, or bottoms out, I guess is what I've been calling it. So thank you very much. I'm sorry I had to skip along pretty fast on some of the slides. I probably should have just started with fewer slides.
Okay, I'm sure we have a lot of questions. I want to start off, though. Alan, is there any way to make a beacon that can illuminate any of these telescopes to calibrate it that way?
You mean to calibrate the antenna?
Yeah, to calibrate the whole system.
I think it's very, very hard to do. You know, you could have a drone and you fly it around, but there's that drone there's going to be reflections from the ground, and it's very hard to get an environment that doesn't have some, in the cellular business we call multipath. Cellular world, multipath is often useful because that's the way you can actually get cell phone coverage. But for us, any kind of multipath you're going to get lots. You'll be able to measure the antenna beam, but there's going to be a lot of.
I suppose I was thinking much higher than that, but.
Well, I don't know. Jefferson, it's possible. Yes, you mean from the satellite? Yeah.
Satellite balloon or something like that.
Yeah. Well, that's a good thought. Yes, I think you're right. From the satellite. Not. I was thinking drone. No, I think from the satellite you're right. You could do that.
Yeah. Mark.
So Alan, why don't we make the ground plane hugely bigger? It can't be that expensive, can it?
Well, it's not dirt cheap, and that ground plane was built by Judd and Cassie Bowman, and they did the welding as well. Yes, it could be. We don't completely know what all. We know things we want to do differently and improve. An even larger ground plane, I'm not really sure is on our list, but yeah, could be. You're right. I mean, we're talking. I think it was in terms of actual panels, maybe $30,000. Not a huge amount of money.
That sounds so cheap.
Do you know how soon the other experiments might have a result that would verify this?
I don't know a lot. I've advertised and got commitments for those groups to all join us at Haystack Observatory in the end of August for a workshop. During that time, we'll certainly know a lot more. I know quite a bit about SARAS-2, which is the India group, and they had hoped to start taking data in this frequency range starting the 1st of this month. Last month, I believe. Anyway, it was, but they're not doing that yet. They're still testing, and they probably won't deploy in northern India for maybe even another month. But if their data is as good as their high band data, they might only, and the RFI environment up there turns out to be okay, then they might get a result within, I would think, a few months. I don't really know. I have looked at, maybe somebody can answer here, on the LIDA data. If you look at what I've seen published of the RMS after you've taken out a fit for the foreground, I have not seen LIDA data that's getting down. I think you have to get down to this level of under 100 millikelvin. But correct me if I'm wrong, if anybody can tell me what you expect, what you've been getting so far.
I think Lincoln is at OVRO now.
Yeah, they're out in the field.
Or maybe
now.
Hugh knows.
They're out in the field right now. Yeah.
We're working on it at the moment.
Yeah.
So Lincoln's on site at Owens Valley doing calibration at the moment. So, but I don't want to give any numbers.
Right. Okay.
I don't know.
Well, if there's anything that we can do, that anything helpful we can do, we would really like to do that. I have also I have looked at the LIDA antenna, and it's very very free of beam chromaticity if you only used the two. But the fact that you're using it as both polarizations, I would like some more. You might want to look at that some more, because I saw something that is not that great. I can show you that later. It's not real serious, but I think that could be an issue.
Jonathan?
Alan, would you mind terribly going back to your very first slide?
Okay. I'll try to figure out how quickly I can.
Yeah, just as quickly as you can.
The very first slide.
Alan spends so much time on video games, it's easy.
I couldn't
Okay.
really, not the title one, the very first title one.
This one, yeah, sorry. I know what you want.
Forgive me, it's a very basic question. I'm not the world's expert on foreground removal, but if I understand this correctly, on the left-hand side, the very top panel is what you actually observe.
Right.
Right. Thousands of kelvins
Yes.
of foreground.
Yes.
Sloping downwards and
Yes.
maybe this is galactic synchrotron or something. primarily, or
This
whatever.
is actually galactic not. This is mostly galactic center below the horizon.
Okay. All right.
It's even higher when the galactic centers are.
So in any event, that is what you model with what you call your 5 physical parameters, is that right?
Yes.
Or your 5 physical
Well,
models?
this is not the raw data. This is calibrated data.
Fair enough. I'll just skip to what my
Yeah.
question is, and it's an obvious one.
Yes.
The second panel is your detection, and that is
Well, hold
the-
on. No, second panel. A second panel is
Residual.
this after we've removed those 5 terms.
Exactly.
Yeah.
So what the second panel then is the difference of a data set consisting of very large numbers, and then you subtracting out large numbers to get
Yes.
very
Yes.
small
You're right.
numbers as the result.
Yes. Correct. Yes.
And that, of course, is worrying, because if what you're subtracting out has some very small signature in it,
Yes. You're right.
or should have some very small signature in it that isn't there,
Yes.
that will give a spurious detection.
Yeah, sure. I mean, yeah.
So-
For example, if there was a ripple, a strong ripple in what we measure,
That's right.
even with taking out these terms, which are all smooth,
Right.
we would see in here, there is a ripple here, but
That's
and
right.
we thought maybe that is our ripple, but no, we can't explain that in terms of being in our system. But you're right. I mean, this could be. Well, maybe you can give us a suggestion of something.
No, I have no suggestion.
But that's what
I
it
guess
is.
what-
You're right. This is what, and you only get rid of this by taking out this.
Maybe what you're saying,
I guess what I'm worrying is that the model, the 5 physical parameter model that you're subtracting,
Yes.
right?
Yes.
Maybe there's something that it should have on a very small scale that is not built into that model.
Well, for example,
what-
I know what you're saying, and maybe it's due to reflection from the edge of the ground plane and so on and so forth, or some kind of resonance on the ground plane, for example. That we have had data where there was a resonance in the ground plane.
Right.
We had some piece of the ground plane which wasn't properly welded or properly connected and formed like a slot antenna, if you will. And we also saw this before we had the receiver below the ground plane, and we had a receiver above, and in some cases we put electrical conducting copper tape around things. We had seen resonances. Yes, you're right. You could have a resonance, some sort of resonance that, let's say this is a resonance. Okay. So one thing that's strongly against that is that if this was a resonance and was changing our chromaticity, then this would go up by a factor of 2 or 3 when we look at the galaxy up.
Yeah. I guess I don't want to go on and on, but you are in the observation you are seeing, in addition to instrumental artifacts, you are seeing true cosmic foregrounds as well,
Yes,
and you do have to subtract those out.
we do, but we're going on the assumption, which maybe is the only way I can sort of say that I don't think that's it, is because everything is smooth. The foreground is smooth.
Right.
Even the ionospheric effects are relatively smooth.
Yeah.
Most everything in our receiver, everything is smooth. So you don't expect this
fine
sharp
feature.
structure.
Right.
And it's really the fact that in fact, if you go back through the memos and things that we wrote on it, the first thing we said, we've got some kind of we've got some kind of resonance or something at 84 megahertz, and then maybe another one down here at about 60 megahertz. And we thought, they were both possibly some kind of still problem with the resonance system in the antenna. And we worked very, very hard to try to identify that, and we figured, well, you know, if we look at another antenna on a different ground plane, you know, what are the chances that we would have the same nasty bad connection or whatever it is that would produce such a resonance, and we didn't see it. So, you know, if we'd just done this with one system without any changes, absolutely we'd be totally, we wouldn't have published anything yet. It's only after we've done all these things, and probably the most important thing now is to see that what we're seeing is global and not really influenced by the strength of the foreground.
Yeah. Thank you very much.
I'm sorry, Erwin, you had a question.
I wanted to sort of spectacular thought. I wanted to change the subject completely to the possibility of dark matter being responsible. If it were, did Barkana at all consider other consequences of such an interaction? That could be empirically checked.
Erwin, I'm not sure I'm the best person in the room to answer that question, but somebody else might. Did you hear the question? You're wondering whether dark matter might explain what we see, but what other effects would dark matter?
If dark matter
Yes.
were to explain what you saw,
Yes.
it would be acting differently from the way we think dark matter behaves now. And what I was asking was, were there any other consequences of such a behavior that could be independently checked?
I don't know that I can answer that. I don't know enough about, to be honest, you know, I don't know enough about, maybe somebody...
So actually, if one of the main points of the Barkana paper and others that came with it is that there's a bulk velocity between dark matter and baryons. So if they are to interact, and the interaction rate has to depend on velocity, this will give you fluctuations. And these fluctuations will be in very large scales. So if you were to see 21 centimeter fluctuations, that will confirm that it's dark matter interacting with baryons.
So you're saying that the people that are doing the mapping to look for the EoR, for example, the HERA project and so on, they would expect to see stronger fluctuations
Yes.
due to dark matter, I think is what he said. And I don't know, at this point, does HERA go low enough in frequency? That's another question.
They have the capability.
But they haven't actually got down that low yet.
We're installing 50 megahertz dipoles literally as we speak. And stuff like that.
So we'll get data, what, in the next few months?
Observing is going to start in October for the low band feeds.
Okay.
And they would have the sensitivity to make that measurement?
I would hope so.
That's aspirational of you.
That's not my department.
David.
So is there anything apart from logistics that stops you putting this experiment on the ocean, so where you'd have very low terrestrial RFI, and you might not need as large a ground plane, if at all?
On the ocean?
Could you repeat the question?
You're asking, is there any way we could put an EDGES antenna out on the ocean? Now, do you mean on a barge or something like that? But the ocean, yeah, the ocean is not a perfect reflector. I can't say I've given this any thought at all. I don't know. To me, it sounds like, you know, the ocean would have to be very, very calm and no waves and.
A tiny island or a defunct oil platform?
I mean, the PRISM group, they're in Marion Island, which is 47 degrees south, and is very free of FM radio RFI. But it's, you know, otherwise it's not much different. I mean, you know, they have a small ground plane. I would worry a little bit about. I think there are some advantages of having a very small ground plane, because then, unless there's rock down a meter or so below that ground, it does make for better lower beam chromaticity. But the downside is that now you have a lot of loss, and you have to be able to, if you want to get back to actually getting, for example, making a decent measurement of the foreground spectral index, you can't easily do that because you've got this huge loss. I mean, that's a little bit of a downside to what Ravi's going to do with his system, because he's not really going to be able to use it to to get an accurate measurement, for example, of spectral index, which is, I think, a nice thing to be able to do with the system. Maybe I don't think it's really important in terms of confirming accuracy, but it is a downside.
Okay, in the back.
What is the reason for dropping the data from 50 megahertz to 60 megahertz in most of the fittings?
I'm sorry, I didn't hear the 50 or 60?
What is the reason for dropping the data in the low frequency range for most of the fittings?
Why'd you drop 50?
The low frequency, look at the diagram on the upper right.
So,
Okay. Well, yes, that's a very good question. We should reanalyze all our data over the wider frequency range, and we definitely should do that. And that is actually sort of in progress, and that's actually part of the reason why I mentioned, I'd like to get polychord. We have done some of that. What else can I say about it? No, I think it should be done, yes. It hasn't always been done. In some cases, though, the data sets with that we've analyzed here with they're not particularly good data sets. There's less data, there's less nighttime data, because we also have to, in most cases, avoid daytime data, and there's some RFI issues, but you're absolutely right. A lot more of our data could be analyzed over the full frequency range, and should be, but it hasn't been done yet.
Any other questions? Okay, I want to add one other thing to Alan's story here. In addition to being a wizard with electronics and a great astronomer, Alan's also a romantic. At lunch, we learned today that he had an early career tagging warthogs in Africa, where, of course, he was raised in Rhodesia. And he would track the juveniles back into their burrows, and there were nets deployed to catch the juveniles as they leapt out, and they would tag them and so forth, and he was working on that. But the romantic part is that I didn't realize that he incorporated this into his honeymoon. And somehow he convinced his wife to go back to Africa with him, and I don't know when you actually told Louise that you were going on a warthog.
She was with us. She partook. In fact, she took a 16mm movie of all this.
Okay, well, there you go. It's a lesson
if I was up to date with the modern world, I would already have that on YouTube.
I would love to see those images now. Anyway, let's thank Alan again.